Hi, Rich Neapolitan back. Today we'll be talking about a fairly simple but extremely important theorem in probability theory called Bayes' theorem. It was developed by the Reverend Thomas Bayes in the 18th century, and it is viewed to be so important that to this day people bring flowers to his gravesite in England to commemorate his life. I say this one of the advantages of living a long time ago is that you can become famous like this for something which is really fairly simple. Disadvantage is you're not alive anymore, so everything has its upside and its downside. All right, let's look at Bayes' theorem. A theorem stated it looks like this. Given two events, E and F, the probability of E conditional on F is the probability of F conditional on E times the probability of E, divided by this same quantity, the probability of F conditional on E times the probability of E, plus the probability of F conditional on not E times the probability of not E. This is set complement, so it means all those elements which are not in E. In terms of logic, it means the logical opposite, not true. Right now I'm using the set theory, a notion of probability, to explain this. Right, let me actually prove this theorem, because the proof is fairly simple. Here's actually, this is another version of the theorem where we don't expand the denominator, and I'm going to prove that first, that the probability of E given F is the probability of F given E times the probability of E divided by the probability of F. All right, owing to the definition of conditional probability, which we discussed last time, we know the probability of E given F is the probability of E intersect with F divided by the probability of F, and the probability of F given E is the probability of F intersect E divided by the probability of E. This is in the chapter in probability in contemporary artificial intelligence, and it can be stated as a definition of actually conditional probability. We then have that the probability of E given F times the probability of F equals probability of F given E times the probability of E. Why do we have that? Well, if we multiply both sides of this equality by probability of F, we get the probability of E intersect F equals this. If we multiply both sides of this equality by the probability of E, we get the probability of F intersect E equals this product. And so since these are the same, because set intersection is a commutative operation, that means this quantity times this quantity equals this quantity times this quantity, and that's exactly what we say here. All right, there I've just written out what I've just said. The proof of equality 1, this equality is now completed by dividing equality 2 by the probability of F. Once we divide by the probability of F, we get the probability of E given F equals probability of F given E times probability of E divided by the probability of F. So this is true, and this is actually one version of Bayes' theorem. To get the version I showed you at the beginning, we simply need to prove this fact, that the probability of F is the probability of F given E times the probability of E plus the probability of F given not E times the probability of not E, which is called the law of total probability. And I'm going to leave it up to you to investigate that or prove it. Again, that is discussed more in the text the chapters of the textbook that I've supplied to you. All right. Let's look at an example of applying Bayes' theorem. Here are those objects that we've looked at before in the last talk. What's the probability of a black conditional on being an A? This is something we haven't quite looked at last time because it's a little bit odd. We're taking all those things which are A's. There's 1, 2, 3, 4, 5 of them. So that's the denominator. How many of them are black? There's 1, 2, 3 of them. So the probability of black conditional on an A is 3/5. Using Bayes' theorem, according to Bayes' theorem, the probability of black given A should be the probability of A given black times the probability of black. Same thing in the denominator, A given black, probability of black, plus the probability of A given not black, in this case being white, is not black, times the probability of white. And these are the numbers that are more natural to us, right? Because we've broken this up into black and white objects. A given black, out of all the black things, 9 of them, 3 are A's, so that's 3/9 or 1/3. Probably black, there's 9 black things out of 13 items, so it's 9/13. This quantity is the same as this quantity. This is the probability of A given white. Out of all the white things, 4 of them are A's, so that's 2/4 or 1/2. Probability of white, there's 4 of them. Out of 13 items, 4/13. And if we multiply by the 3's, can't do some cancellation, you can show that this comes out to be 3/5. So here we computed this conditional probability directly, simply by taking all the objects that are A's, 5 of them, and realizing 3 are black. Here we did it using Bayes' theorem. I'm just illustrating that, in fact, Bayes' theorem is correct. All right. I've illustrated this with this example, but it's really not all that exciting because we can do it directly. I mean, it's not that exciting to do it. It was just for the sake of illustration. I want to get to more interesting examples now. Remember I talked about random variables last time. I'm going to go back to that random variable notation, so let me remind you again what that means. For a deck of cards, you could talk about a random variable suit, and it means whether it's a club, diamonds, heart, or spade. So probability suit equals club equals 1/4. Probably suit equals heart equals 1/4. Probably suit equals spade equals 1/4. Probably suit equals club equals 1/4. So a random variable, again, is a variable that has a set of mutually exclusive and exhaustive alternatives. So the probability of it equaling each of those alternatives adds up to 1. You can do this you could talk about the probability of the set of clubs, right? But here we're talking about a variable taking a value, and we'll see very shortly why that makes more sense in real applications. Suit is called a random variable. And here is an example of why we want to use random variables. We're talking about a population of people, actually in the state of Indiana, I think, having HIV. So HIV is a random variable. And the probability HIV equals present in an individual in this state is 1 out of, what is this? This is 1/10, 100, 1,000, 10,000, 1 out of 100,000. All right? Probably HIV equals absent is 0.99999. All right? So this means out of every 100,000 people in this state, actually this is men in the state, because you'll see shortly. So every 100,000 men in this state, 1 of them has HIV. All right, so let's see what the value of this is and what this has with Bayes' theorem. I just wanted to note here what random variables are again. The state of Indiana requires everyone who wants to get married to take a routine blood test for HIV called ELISA. Joe takes the test because he wanted to get married, so he took the test. He's just the guy who planned to get married. And it comes back positive. And when we talk about tests being positive, that doesn't mean it's a good thing unless it's something you want. I mean, you don't want, so it doesn't mean it's positive news. This means the test was positive. It means it indicates that you have HIV, so the news is negative. But does Joe have HIV? Well, the probability ELISA equals positive, note the random variable notation, given that HIV equals present, is 0.999. This means out of every 1,000 people who have HIV, 999 test positive. If this was a perfect test, this number would be 1. It means everybody who has HIV would test positive. This is called the true positive rate. Remember, I mentioned this in my last talk, the true positive rate. The probability ELISA equals positive given HIV equals absent is 0.002. This means out of every 1,000 people who do not have HIV, 2 will still test positive. If it was a perfect test, this number would be 0. This is called the false positive rate because it's positive, but it's false because these people don't have it. Now, Joe tested positive. If this number was 1 and this one was 0, it would be a perfect test and it would mean he has HIV. But this number is not 1 and this number is not 0. And note that neither of these numbers are the probability that Joe has HIV. It's the probability of a test result. What we need to know is the probability of Joe having HIV, which means we need to know the probability HIV equal present, conditional on Eliza being positive. We need to reverse these two, because we know Joe tested positive, and we want to know the probability HIV is present. Remember, the prior probability HIV is called a prior probability because it's the probability before we obtained any new knowledge was 1 out of 100,000. All right? That's what I just showed you on the previous slide. In order to know the probability of HIV being present given ELISA is positive, we need this number, and this number. Let's go on now. So I got rid of the HIV equals present given test equals positive because there's not room to write this. But that's what it means. Probably HIV is present given test equal positive equals the probability of positive given present times the probability of present divided by this quantity again, plus the probability of positive given absent times the probability of absent. These are the numbers from the previous display. This is the true positive rate. This is the prior probability. 1 out of 100,000 men in this state who take the test to get married have HIV. This is the same number as that. False positive rate. All right. And this, out of every 1,000 people who don't have HIV, 2 will still test positive. And this is the prior probability of not having HIV. This number comes out to be 0.005 approximately. And it's somewhat surprising that it is not very likely that Joe has HIV. I mean, when you initially saw this test, which seems to be pretty accurate, you might think, well, this guy probably has HIV. And quite a few people who deal with these tests think like that. But if you get nothing else out of this, my 2 weeks of this course, I want to impress upon you the importance of understanding prior probabilities. That the probability of an event is based on our complete information about the event. And our complete information is not just the test and how accurate it is. It's this prior probability of Joe having HIV, and since it's so small, this number comes out to be pretty small. All right? And what does this mean in a relative frequency sense? It means out of every 1,000 men who take this routine blood test in the state of Indiana because they wanted to get married and test positive, that's what we know about them, only 5 have HIV. And so based upon the information we know about Joe, the probability is 0.005. I mean, Joe either does or does not have HIV. So the probability is really a measure of our information about him. It's not a property of him. Again, this number is not ridiculously small. His probability has gone up quite a bit. It went from 1 out of 100,000 to 0.005, and he does warrant having additional tests. But in the meantime, he should be able to relax a little bit and not feel like he almost certainly has it. All right, to further impress upon you the importance of prior probabilities, let's look at another example. This example I actually made up. Those numbers in the previous example are about a real test. But these numbers seem reasonable to me, and they do make my point. Suppose a certain pregnancy test has exactly the same accuracy as ELISA, and Mary takes that test and it comes back positive. Is Mary pregnant? Well, the probability, if it has the same accuracy as ELISA, the probability the test is positive given pregnant equals yes is 0.999. Probability test is positive given pregnant equals no is 0.002. So this is information about the test, but is not the probability that pregnant equals yes, which is what we need to know, conditional on the test being positive. Again, we need the prior probability to get that. Now, what is the prior probability of Mary being pregnant? Mary was not just somebody who flippantly took a pregnancy test. I mean, people who take pregnancy tests are people who believe they might be pregnant for other reasons. So this prior probability is reasonably high. In this example, it's 0.2. It means out of every 10 people who take a pregnancy test, 2 are actually pregnant. When we plug these three numbers into Bayes' theorem, we get that 0.00001 is replaced by 0.2, and this comes out to be almost 0.93. So again, the accuracy of the test by itself doesn't really have much to do with what is the I mean, there's a lot to do, don't get me wrong, but it's not the whole story about the probability of having HIV or being pregnant. This is a high probability, and it means out of every 100 people who take a pregnancy test and have a test positive, about 93 of them are in fact pregnant, which I think, I guess I made this example up, but I think these numbers are pretty reasonable. All right, that's actually the end of Bayes' theorem. It's a fairly short talk, but Bayes' theorem is so important, I thought I would devote a talk to it.